Hello kids, I will be reviewing some of the past paper questions for the presentation I gave regarding thermal properties and temperature. So let's look into this question. A student wants to investigate good and bad absorbers of thermal radiation, and we do understand that the surface really comes into effect. The dull surfaces will absorb more heat, and shiny surfaces they reflect heat, so it would be harder for those to increase in temperature if we try to heat them up using radiation. So a student has the following apparatus. It's a small polished can which is black painted. The one is polished, the other one is black painted, so it's dull. We've got two thermometers and an electric heater. So explain how the student can use this apparatus she has available to carry out her investigation. Describe the results she would expect to obtain, and draw a diagram of the setup. Right now, I'm going to draw uh, this the apparatus what you can do. So we're going to place the electric heater right over here. Just please don't mind, I'm doodling right, so it may not look very good. So what now over here, uh, a supply of cold water. Now this is a very important question and a meter rule, right? So I'm going to have these two, uh, this and this sample in the beakers at equal distance. I'm going to place the meter rod at the base, right? Place the electric heater at this in the middle, and the other beakers at the sides at equal distance from the electric heater. I place one thermometer over here and one thermometer over here, and I put my shiny one over here, the shiny object can, and the black can, which I'm going to just shade a little bit like this, right? So this is how I'm going to set up this experiment. Why? Because once I heat up this heater, radiation is going to move in both directions, right? Like this, in both ways at equal distance. So we can expect equal amount of heat to be delivered to both of these beakers, except the one with the polished surface will reflect back heat, most of its heat, and the temperature of this beaker of water, supply of water, as we have supply of cold water, will not heat up much, but the water in this beaker B will increase more, because this dark or black painted can is not going to reflect heat, instead it is going to absorb the heat, right? So how can I explain this question? I'm just going to answer this. We can say she can set up the apparatus, right, as drawn in the figure, right, above. Once the electric heater is turned on, uh, radiation will be absorbed. Oh, sorry, the A is not working. Yeah, the radiation will be absorbed by both the water beakers, except the fact that the can with polished surface will reflect most of the radiation, and the water of that beaker will have slight rise in temperature, right? Compared to this, the beaker with black painted can will have greater rise in temperature, because black surface will not reflect incoming radiation energy, right? Hence the water will increase faster. So you can express this in many ways. You can even express the experiment. I'm not going to express this because I'm going to put in markings. Let's say this is at 0. I mean, if you make a well enough diagram, I mean, don't go on the appearance of this diagram, but how you define this diagram. For example, I'm going to say that this is the meter rule. I'm just going to use MR. You should write complete that this is the meter rule. This is at 50, which is the middle. I'm going to draw this dotted line through the middle of this electric heater to show, and I will mark this as 100, that this is at 100, which is going through the middle of the can, and I will mark this as 0, and the line going through the middle of the can. This definitely, the figure itself is now showing, and I just need to mark this that this is a thermometer, right? Beaker with water. You just need to give some description. Now once you give complete description of the diagram, that would help you focus more on to the technical points that you need to discuss, right? Describe the results you would expect to obtain, right? So 4 marks are there for the explanation of what she is going to expect from this experiment. What I actually see in these answers when I ask this, give this question to students, they actually care more to explain how the experiment is being done rather than what she's supposed to expect as an answer. And once they do not provide complete description of their observation. And remember, 4-point means I need to have a specific understanding of why this is happening, and why these two beakers are at different temperatures after a while. And if I start on use this answer space for explaining how I'm setting up the experiment, then I will have very little space first of all to write my answers. And I see some of the students going down the line, and some of them covering this even the marking area. So please don't do that, because we need to be we need to attempt the paper very neatly. So instead of writing more about the experiment, try to draw the experiment with well enough description on the diagram, that this is the thermometer, this is the water with the beaker, this is the can with black paint, this is this can. Just label it properly and use this meter rule and mark it properly, that these are at equal distance. Just by the diagram you can see that if shiny can is at 0, the heater is at 50, and the black can is at 100, then we can easily say, any observer can tell you that this is having equal distance in between them, the 50 centimeter here, 50 centimeter here. So I don't need to explain this. Instead, I'm just going to express what the heater is going to do, and how the radiation is going to be transferred, and how the temperature is rising in one and not in the other. So that will award me complete 4 marks, instead of just explaining the experiment, where I'm going to lose more marks if I don't express the observation. Instead, if I express the experiment only, right? So keep this in mind, that you don't need to go into explanation much, because they already told you that draw a diagram of the setup, right? So the diagram should be well clear of what you're doing as an experiment. Just give the answer to the question, right? Okay, moving on to the next question. A beaker contains some water at room temperature. A student places a mercury in glass thermometer in the water with the bulb of the thermometer just beneath the surface of the water. Shows this arrangement. Now this thermometer is not fully immersed in water, right? Keep that in mind. This is something to note, that this is not fully immersed. We usually immerse the thermometer inside. Now we're just keeping out of the top. The student uses an electric fan to blow air across the open top of the beaker, right? There's a fan that is going to now blow wind, and we do know this, since this is an open beaker, when we are going to increase the airflow above the beaker, then the vapors are going to flow with it. That would increase the rate of evaporation, and that means evaporation, we do know, causes cooling. So the increase in the rate of evaporation means increase in the fall of the temperature, right? The temperature will fall faster. So she noticed that the reading of the thermometer begins to decrease, right? Explain in terms of water molecules why the temperature of the water at the surface begins to decrease. Now uh, uh, liquids evaporate at temperature below boiling point, and uh, evaporation is directly related to uh, air flow above the container. Greater air flow results in faster evaporation. Evaporation causes cooling, so in this case cooling will be faster due to water molecules escaping at a faster rate, right? So uh, uh, explain in terms of water molecules why the temperature of the water at the surface begins to decrease, right? So we do know liquid boiling point, and we need to add this at liquid surface, right? Just add this now. Yeah, that completes an answer. So when we discuss this, right, uh, let me just space this up properly. Okay, I think there we go, right? So that is a more plausible answer to this question, right? So liquid evaporates at temperature below boiling point on liquid surface, right? So surface, we have discussed the surface, and evaporation is directly related to airflow. So we are discussing what she is observing. Greater airflow results in a faster evaporation. Evaporation causes cooling, so in this case cooling will be faster due to water molecules escaping at a fast rate. So we have discussed what in terms of molecules we're supposed to discover why the temperature of the surface will decrease, right? Although I've given extra information, but again this is for 3 marks, so we need to have some elaborative answer to this question, so keep the marks in mind, right? Okay. The student places thermometer near the bottom of the beaker. The electric fan continues to blow air across the top of the beaker. After some time, the student observes that the temperature of the water at the bottom of the beaker is decreasing, right? The student will continue to blow air, but the student will now notice that the bottom is also getting colder. State the name of thermal transfer method causing this and explain what is happening in water. Now we do understand that in liquids or fluids, we're going to call fluids. Why fluids? Because fluids take into account both liquids and gases. So I always use the term fluids instead of just using liquids or gases, because in this case we're just generalizing the facts. So fluids transfer heat using heat through convection, right? And what is convection? In convection, fluid molecules transfer energy through their collisions and movement, right? Hence the cooling effect will reach the bottom of beaker due to convection, as higher or higher energy molecules keep moving towards the top to escape, hence lowering the temperature, right? So that's explain what is happening in water. So state the name of thermal transfer method. We have given the name, which is convection. Fluids transfer heat through convection. Uh, right, and explain what is happening in water. So we have also discussed what will happen. I'm not using the term water, I'm using a generalized term of fluid. In convection, fluid molecules transfer energy through their collisions and movement, hence the cooling effect will reach the bottom of the beaker due to convection, as high energy molecules keep moving towards the top to escape, hence lowering the temperature. So we have discussed. So again, this was for 3 marks, so remember that marks really do come into account, right? Now, thermometer is used in the experiment has a small range. No, this topic is now removed. Sensitivity of the thermometer or thermometer is no more there. So I'm not going to go into this question. As for syllabus 22, 23 to 25, sorry, is going to not have these range and sensitivity questions anymore, because this topic has been removed from the content, right? Okay, moving on to the next one. Describe in terms of molecule what happens when a liquid evaporates. Now, in terms of molecules, we do understand. Again, we discussed this, that where we had this conversation about boiling and evaporation, right? We had all this jumbled up slide in which we discuss evaporation. So what happens in evaporation? We know this, right? Just describe this in your own words, but remember this is 4 points. So mention the liquid surface, the factors that will affect, also why cooling is going to happen, because higher energy particles leave, so leaving the total energy of the liquid lower compared to the previous one. So do discuss at least 4 of these important distinct points. Do not repeat a point and consider that that is going to get you scored. You need to discuss at least 4 distinct points regarding evaporation, right? Liquid evaporation. So it could be the surface, it's done through the surface, it's on the lower temperature than the boiling, can be done at any temperature below boiling point, accelerates when the ambient temperature is higher, accelerates when the area is higher, and so on, right? So you can express this answer, so I'm not going to write this. Now, this is a fun question. Figure 4.1 shows wet clothes drying on a washing line in an outside area. State 2 changes in the weather that help the wet clothes to dry more quickly, right? What 2 weather conditions are going to increase? We just discussed that one is going to be the ambient temperature, and since this is outside, so we cannot change the area since they're already hung properly. So I just cannot expand this. So we cannot discuss the change in area, but instead we're going to use the third factor, which is the wind speed, right? If you remember, we had 3 factors: area, ambient temperature, and wind speed. Since they're hung, so we cannot discuss the area, but instead we're going to state 2 changes in the weather that may help. So just you need to state the names, right? We just stated that. So 2 marks for just 2 names. No need to explain this whatsoever, right? Now moving on to the next question. A student in home, there is wood burning stove made out of iron. The mass of the wood is 85 kilograms. Now we have mass. State what is meant by thermal capacity of an object. Now please review what we discussed is the thermal capacity, right? Thermal capacity was different from specific capacity. So thermal capacity is it is the amount of energy for every 1 degree Celsius rise in temperature of a certain mass, right? So this is how you can express this, that what is thermal capacity. It is the amount of energy required for a mass. Take care. And I'm not going to say per a specific mass, because that would be specific heat capacity if I restrict the mass. So in this case, in thermal capacity, mass is not restricted, right? So it is the amount of energy required for a mass to rise its temperature by 1 degree Celsius, right? That's just one mark answer, right? Okay, specific heat capacity of this is this. Calculate the thermal capacity of burning wood. So we do know M is equal to 85 kilograms, right? That is M. Then we have thermal capacity, specific heat capacity, which is 460, right? joule per kilogram, sorry, per uh, kilogram Celsius, right? So thermal capacity, right? I'm going to call it thermal capacity as a whole is going to be M multiplied by C, right? And that would be in this case equals to 85 multiplied by 460, and that would be our answer. Let me just pull my calculator up, right, real quick. So, oh, there you go. Where is it? Okay, let me just close this. Okay, I think something's blocking the view. Okay, there we go. So we have this over here, right? Oh, somehow the calculator doesn't want to show up over here. So I'm just going to calculate 85 into 460. So it would be 85 into 460, that is 39100 joules. So that would be the answer is going to be 39100 joules, or I can call this just 3.91, right? And by kilojoules it would be or I can say 39.1 kilojoules, right? So either way we can write this answer. So I hope I'm able to clarify some of these questions. This is also an experiment based question. I did not discuss this because I've already discussed a similar question in slide. So this experiment over here, how this runs, so I'm just going to skip this question for now. But this is how you're going to solve these questions, right? I hope I'm able to clarify some of the problems and how to attempt these questions. Thank you.